All right, welcome to 2.9, solving inequalities in one variable. Before we get started, there's a quiz tomorrow on 2.6 and 2.7. 2.6 and 2.7 won't include 2.9. Okay, so for example 1, we want to find where a polynomial is 0, positive, or negative. And it says let f of x equal this polynomial. We want to determine the values that cause f of x to be 0, positive, and negative. So the first thing we're going to do is we're going to figure out where f of x is equal to 0. In order to figure this out, we set f of x equal to 0 and we solve for x. We're literally finding the zeros of this polynomial function. Now, because this polynomial is factored, it's pretty easy to just look at it and see where we have x values that equal 0. So when x is negative 3, y is 0. When x is positive 4, y is 0. The middle factor, if you set that equal to 0, you're going to end up with x squared equals negative 1, which just isn't going to happen. So we're only looking at two real zeros, right? So let's go ahead and plot those on the number line to determine where our graph is in the positive and in the negative. Okay, so now we have negative 3 and 4 on the number line. Those are the values that cause 0. And at this point, we want to figure out where we are in the positive and the negative. So let's go ahead and plug in some values. Let's plug in values prior to negative 3, like a negative 4, maybe. And plug in a value in between negative 3 and 4 like 0, and then plug in a value after 4 like 5, and that's going to tell us what our graph is doing, whether it's in the positive or the negative. So the first thing I've done is I plugged in negative 4, and that tells me here that this factor is going to be negative, minus 1. This factor here, we have a 16 plus 1, that gives us a plus. And then this factor over here, we have a minus 8 to the power of 2. Anything to the power of 2 is positive. And so that tells us that prior to negative 3, our values are negative. Negative times positive is negative. Let's plug in 0 and see what happens. So plugging in 0 gives us a positive value. So that tells us anything that we plug in between negative 3 and positive 4 results in a positive value. So let's focus on after 4. I'll plug in 5 and see what happens. Okay, so I've plugged in a positive 5, and I end up with a positive value here. So anything I plug in after 4 is going to result in a positive value. So what we want to do now is address the part B and part C. We want to identify where the graph is positive and then where the graph is negative. So we're in the positive from negative 3 to 4, and then from 4 all the way to infinity. And you guys notice how I didn't include the zeros there, because it just says where it's positive. 0 is not positive, so I didn't include those zeros. We are in the negative from negative infinity all the way up until negative 3. So far, so good? Yep. You guys, we could have done that much faster, much easier, based on what we know about the leading term. What is our leading term of this polynomial? If we were to multiply these binomials together, the leading term, we'd have an x times x squared, and then this is going to be an x squared here. So we have x times x squared times x squared. That's going to result in a positive x to the 5th power, right? The leading term tells us about the ending behavior of the function. So because I have a positive leading coefficient, I know that as x increases, the y value will increase. So after this last 0 here, as x increases, y increases. We're in the positive here, right? Now, because the degree is odd, as x decreases, the y value will decrease. We have the split ending behavior, right? So if we're positive on this side, we're negative on this side, right? Split ending behavior. And At -3, we have a 0, and that's a multiplicity of 1. With an odd multiplicity, we go right through. And then we come back to the 4 here. At 4, we have an even multiplicity. With even multiplicities, we bounce off the axis. So we can look at the graph here and say, oh, well, these are y values that are in the negative, x values that result in negative y values. These are x values that result in positive y values. These are x values here that result in positive y values. So we could have done this just by what we know about the leading coefficient and the degree and the zeros of the function. You guys with me there? Yep. But plugging in will always work if you forget. So the next problem here, we're trying to figure out where this polynomial is greater than 0. Where is the polynomial greater than 0? This one's a little bit more difficult this time around because we actually have to break it down. We have to figure out what the factors are. We have to figure out the factors so that we can identify the zeros so we know where the polynomial is actually equal to 0. So this one's a little bit of a pain to break down without a calculator because we take the factors of that constant over the factors of the leading term, and we end up with a ton of different possibilities. And we would have to synthetically divide with all of those to figure out which one would actually work. The one that actually works is 4. All right, let's just break it down. Okay, so break it down with 4 and synthetically divide. So breaking down with the 4 tells us that x minus 4 is a factor. We started with a power of 3, and so this quotient here is 2x to the second plus 1x minus 6, which is, we're trying to figure out where this is greater than 0, right? And at this point here we have a binomial times a trinomial. We need to figure out how to break down this trinomial, right? It is factorable. So this is our breakdown so far. This tells us what the actual zeros are, what x values cause 0, because we have the factored form. And we have 1 0 at -2. We have another 0 at 3 over 2. And we have another 0 at 4. Another 0 at 4. Now, you guys could go through and you could plug in values prior to -2, and between -2 and 3 over 2, and in between 3 over 2 and 4, and then after 4, and figure out the signs. You could do it that way. Or you could just rely on the leading term and see what the leading coefficient tells you and the degree tells you. The positive 2 tells us as x increases, our y value increases. So as x increases, our y value increases, right? We also know that because it's a degree 3, we have that split ending behavior. So what you guys couldn't see who are listening to this on YouTube is I was doing the thing with my arms, right? Split ending behavior. Was that terrible? I was trying to be funny, but it was not funny. Should I like stop now and go back over it because it was that bad? Or should I just let them hear the bad joke? Yeah, they can hear this. Just keep going. We're running out of time. 15-minute time limit. Okay, so we know that because we have the split ending behavior, as x decreases, our y value will decrease. Each one of these zeros is a multiplicity of 1. We just go right through them. So what that tells us here is any x value we plug in prior to -2 is going to result in a negative y value. Any x value that we plug in between -2 and 3 over 2 is going to result in a positive y value. Any x value we plug in between 3 over 2 and 4 is going to result in a negative y value. Any x value we plug in after 4 is going to result in a positive y value. So that brings us to solving this inequality. Where do we have values that are greater than 0? Where we're in the positive. So any x value that I plug in from -2 to 3 over 2 results in a positive y value, in union with any x value we plug in from 4 to infinity will result in a positive y value. That gives us the solution for our inequality. So far, so good? So on this problem here, example number 5, we want to figure out where this rational is greater than or equal to 0. And I think the best way of understanding this is just graphing the rational function and then seeing where it's actually bigger than 0. In order to graph it, we have to go through the different things. We want to think about the horizontal asymptote. We want to think about the vertical asymptote, the x-intercept, the y-intercept. So let's go through that series of steps to figure out all the essential things that we need for this graph. So first of all, the horizontal asymptote, I have an x to the first power over x to the second power. When you have a degree in your denominator that's greater than your degree in your numerator, then you have a horizontal asymptote right at y is equal to 0. So the next part here, I see that I have division by 0 at -3 and +1. So I have a vertical asymptote right at -3 and +1. Let's figure out what our x-intercept is. And remember that we find the x-intercept by setting the numerator equal to 0. That's like setting your f of x equal to 0 and then just solving for x. So if you solve for x here, you would subtract 1 to both sides and divide by 2, which would result in a -1/2 for x, right? So we have when x is -1/2, y is 0. That's a point right there. I'll use red instead. And then let's figure out the y-intercept. What's our y-intercept? How do we find our y-intercept? What do we plug in for x? 0. So if that's 0, if that x is 0 and that x is 0, and that x is 0, we're left with a 1 divided by 3 times -1, which is a 1 over -3, which is a -1/3. So when x is 0, y is -1/3. Y'all with me so far? All right. So we have 2 points. We know we go through those 2 points. And we're going to approach the asymptotes. And I know that because I'm going down a -infinity here, I'm going to come from positive infinity here. And because I'm going to positive infinity here, I'm going to go down to -infinity here. So this is my graph so far. And I want to know where I'm in the positive. Where do I have positive? Where do I have x values that result in positive y values? Right here. Right here. So that solution consists of the x values from -3 to -1/2. Not including the -3 because that's a vertical asymptote, but including the -1/2 because that gives us a 0. So we're including it because this says or equal to. And then we're also going to be able to plug in x values from 1 to infinity that result in positive y values. So this here is our solution for this particular problem. Okay? Are we good on that? So to address the previous slide that I didn't really like, what it asks for is to determine where we're at 0 and undefined. We're looking for where we're at 0 and undefined because where we're undefined, that marks a vertical asymptote, and where we're at 0, so the vertical asymptotes and the zeros mark the boundary where we can go from positive to negative on a graph, essentially. Okay, so that's why they're having us look for undefined and zeros for this example. I just thought it was a little bit confusing to go from this one to the other one. I figured the graph would be easier to understand. Is that Good assumption?
Yeah.
Yeah? All right. 5, 4, 3, 2, 1.